The study of weather is an essential practice that can help predict not only the environment, but the fate of people, infrastructure, businesses, and essentially anything on Earth. With the current looks of things, weather patterns are inevitably changing rapidly, and a device will be needed to analyze and forecast the effects it may have on local populations. Here we have our proposal of a device that operates around the globe collecting data on current and future weather conditions. As a result, we come up with the following design: a device that operates on manipulating buoyancy relative to air while using a solar cell to store potential energy required for our design subcomponents.
We've done a lot of research and calculations that analyze our design in order to determine certain requirements and the expected performance of our design. Due to the lack of time, I will only be talking about two calculations we performed to analyze our design. First, I'd like to talk about the lifting gas. The lifting gas provides the force that holds our device afloat. The lift force is simply a buoyant force of a lighter gas relative to air. We can consider lift to be a quantity relative to respective molar masses. We use hydrogen and helium because they are both lighter than air. As you can see, hydrogen provides 1.2 kilograms per meter cubed of lift, and helium provides 1.11 kilograms per meter cube of lift. The second analysis we performed for our design was the mass analysis. Using Hypalon as the balloon material and doing some initial calculations, we determined that the volume of the balloon needed to hold the amount of gas required to lift the device is approximately 52.136 meters cubed and has a radius of approximately 2.5 meters. The entire problem is one huge optimization problem where the mass of the vehicle is dependent on energy, lift, buoyancy, and altitude constraints, and every constraint is also dependent on the size and mass, which we're trying to find. However, calculations prove that indefinite flight of this vehicle is possible at all altitudes. The ratio of lift to weight of the material will increase as the sphere gets larger.
On the outside of the finished balloon, the only things to take note of are the solar concentrator and a propeller. The solar concentrator is used to generate power for the device, and the propeller is used to rotate the device around the ground plane axis. The inside of the balloon is far more interesting. Not only is it full of the lifting gas, but it also has a series of 4 gear motors around the periphery. These gear motors are attached to a weight in the middle. This weight is the battery using its weight to achieve a purpose. The 4 motors are attached with strings to the battery, and they work in conjunction to move the battery around the inside of the balloon. This changes the center of gravity of the balloon, allowing it to point in different directions. The reason we chose this way of aiming the device is because it's far more energy efficient and stable than using propellers alone. An electrolysis apparatus and condenser apparatus will also be in the balloon. These are used to replenish hydrogen lost to diffusion through the balloon material. This regeneration of hydrogen allows the balloon to fly indefinitely. Additionally, on the inside of the device would be air compressor tanks used to change the mass of the device and control altitude. Seeing as how the flight of a balloon isn't very interesting, we decided to focus on motion control for the prototype. So I have this motor hooked up to an optical encoder, which I'm going to use to measure position. And I also have an Arduino program that's going to measure position and time, and using those values, we'll be able to correlate speed to voltage. Very smooth motion here. Using this data, I was able to model the output of the motor. Feedback comes from these little Hall effect sensors, and when the magnet changes its angle, this wire here outputs an analog voltage that is dependent on the angle of the magnet. Turning the output of this sensor into a positional output was extremely difficult, especially because the signal is very noisy. Eventually, I was able to tune the motor's response with a high degree of accuracy. We got the speed up to 99% of the desired output, and positional accuracy was within 10%, under no load. We formulated equations to represent the cable length versus where the battery is inside the inner circle. Taking the derivative of this equation gives us the velocity of the string as it changes length. I made a test string by bending flat bar around a tire and welding it. This device was extremely complicated to build. I don't have time, even if I took the whole video, to begin to unpack what's in there. 5 microcontrollers, 2 boost converters, 2 motor controllers, 5 positional sensors, 4 motors. The list goes on and on and on. There were several reasons why the device didn't work as expected. The noise of the sensors was the biggest issue. Under the torque of the weight of the battery, the noise on the sensors really messed with all the algorithms tracking motion. It was almost impossible to work around this. Another interesting development was learning how to change a unidirectional ESC into a bidirectional ESC by using a relay to switch around two of the phases to the brushless motor. This concludes our final project video. I hope you enjoyed.